Okay, good morning. A couple of things here. I gave you that chain rule thing. How'd that go? Any issues with that? No? Did you find it kind of helpful just to go through it and make sure you know what you're doing? Yeah? Please just, if you have it, hand them in down to the center aisle. I'll come pick them up. And then I have something for you. So, there's a huge stack of stuff here. I want you to take 4 of these. All right? There's 4 pages, identical pages. Just take 4 of them, pass the stack around, okay?
Is it cool if I email you the paper? I just have it on my other notebook.
Yeah, that's fine. All right, you know what? I'll expedite this. I'll take 4 of these, pass them down. Take 4 of those, pass them. Take 4 here, pass it down. There you go. All right. Okay, so here's what we're going to do. We're going to start class today with a problem that's related to what we did last time. Do y'all remember what we did last time? Yeah, last class. We did this thing called implicit differentiation. Implicit differentiation, all right? That's what we did last time. What we learned is that when you take a derivative, it now matters, what variable you're differentiating with respect to, right? We have extras? Extras? Okay, so I say, for the extras, I say take another 2 of them, then pass the packet around. Yeah, I printed 120 of them, so take an extra 2 or 3. All right, so last class, it's important for us to understand, what we're differentiating with respect to, right? So let's do a warm-up problem. I want us to find dy dt if I give you the equation x squared plus y squared equals 400. All right? So just as an interpretation of what's happening or what we're doing here to try and interpret this, we're given some equation, right? It relates 2 variables together, right? It's a relationship between x and y. And I'm asking you, what will be the instantaneous rate of change of y if I change the variable t by just a little bit, right? So if I nudge the value of t just a bit, how much will the y value change? And one thing that you should, I guess, see in this is that the variable that we're differentiating with respect to, what is the variable we're differentiating with respect to here? T, okay? Notice that the t does not appear in the original equation, right? Like t is not a variable in the original equation. But that's okay, we can still do this. So we're differentiating with respect to t. And that means nowhere in this, when I differentiate, nowhere will I ever get a 1 when I do the chain rule. I'm never going to get a dx over dx. I'm never going to get a dy over dy because everything's going to be with respect to t. All right? So let's differentiate. We differentiate the left side and the right side. So this looks like this. We're taking the derivative with respect to t on the left side of the equation. And then we're taking the derivative with respect to t on the right-hand side of the equation. We'll start with the easier side, right? The right side, the derivative of 400 is what? 0, because derivative of a constant is always 0, right? Okay, here I have an addition between 2 terms, right? Addition. So I can do them individually. So I need to take the derivative with respect to t of x squared, and then plus the derivative with respect to t of y squared. Now, when I take the derivative with respect to t of x squared, I have to apply the chain rule, right? So first I have what? 2x, right? So first I have 2x, and then times, now here's the chain rule, right? We have to take derivative of the x with respect to t, right? Which is dx dt. And I'm actually really happy to see this. Well, no, I'm not happy to see that yet. Sorry. I forgot what I was asking for. I'm asking for dy dt. So let's keep going, right? Any questions here? Plus, now this is going to be the exact same thing, right? 2y, and then we have to multiply by the derivative of what the y is with respect to t, which is dy dt. And so I'm done with the derivative here, and I have equals 0. And now I'm happy, right? I'm happy because the thing that I'm solving for, right, the thing I've been asked to find is actually appearing in this new equation, right? This is an equation. At the end of the day, this is an equation, right? And so I have an equation that has the thing I'm solving for. So let's isolate this by itself. So let's move 2x dx dt to the right side. So I'll have this 2y dy dt equals negative 2x dx dt. And then lastly, I can divide everything by 2, right? Question? No? You're right? Okay, so dy dt equals divide, by 2y is what I meant to say. Divide the left and right hand sides by 2y. And I guess we could get rid of the 2's and be left with the final answer, dy dt equals, let's see, negative x times dx dt over y. There it is. I have solved for dy dt. Any questions there? Are there any extras? Where's that stuff I passed around? Are there any extras now? Yeah, there's some here. Good. Let's see, who does not have, I just passed these out, so we're going to use this today, just for now, just look at it. Go. One more, back here. There you go, you get this big old stack, it's yours. All right. All right, so back to what this means. This means if we were to change the value of t just a little bit, right? The change in y would be equal to negative whatever the x value is divided by the y value, but you also have to multiply by this, which is the amount that x would change if you nudge the t a little bit. All you need to know here is that what we've done is we've somehow taken the rate of change of y, the y variable, the rate of change of y, with respect to t, right? We've taken the rate of change of y with respect to t, and we have somehow connected it, right? We've connected it to the, what is this? The rate of change of x with respect to t, right? We have taken the rate of change of one variable, right, and related it to the rate of change of another variable, right? Two rates of change now have a relationship between them, right? That's what this next section is called, right? This next section that we're about to start, 2.7, is called related rates. And it's exactly what I'm just trying to explain to you. We have created a relationship, right, between two rates of change within an equation. You change this, you have a little bit of change here, and this is the impact is going to be felt over here. So there's this relationship, right? Okay, so still right now it doesn't make a lot of sense what we're about to do, all right? So I'm going to bring up the notes, we're going to look at them briefly, and then we're going to get down to our first problem. So the notes for this section start out, and you can read, I'm sure, but I'm still going to bring them up. Hold on. There we go. I'll read this to you. Oh, geez, come on. All right. Related rates. We have now reached one of the most exciting and useful sections of this course. We now study the applications of differentiation to related rate problems. This will be one of the most challenging sections of the course. Students often struggle with this section because it involves word problems. I admit these are intimidating at first, but I assure you that there is a somewhat of a systematic approach to these problems, and once you figure out how to translate the word problem into the math, things will start to get better, and you might actually start to like this. I don't know, but maybe you might, all right? As you will see, there's an expectation here that you're going to know some basic geometry, trigonometry, formulas for areas, volumes, etc. Right? So as I work through this, there's going to be things that we're pulling from different classes, like, oh, remember that the area of a circle is pi r squared. Oh, remember what similar triangles are. Oh, remember the Pythagorean identity. All these different things. What's the volume of a cylinder? All these different things we're going to be pulling, all right? So there is an expectation that you know these things. Don't hesitate, if you're at home working on a problem, to just Google a formula if you don't know what it is, all right? So we're going to begin slowly, and we're going to work our way to more advanced problems, all right? Now, as far as a procedure, I gave you a piece of paper here. Can I steal one of these? So what you'll see here is this is available to you in our formula sheets online. Okay, this is there. It's called the Related Rates Worksheet. You can print out your own copies of these, and you can bring them to the exam. So if you want to use this blank paper on the exam, you can. I won't provide it to you, though. All right? So you have to bring this if you want it. What this is kind of a template to set up these problems. Now, this template doesn't always work, but it's at least a good place for us to start in this class, right, with these problems. So what we're going to do, and it's not going to make a lot of sense when I tell you what we're going to do until we do a problem. The first thing we're going to do is we're going to draw a picture, then we're going to draw a second picture, then we're going to write down what we're given, then we're going to write down what we want, then we're going to find an equation, then we're going to differentiate it, and then we're going to solve the problem. I mean, that's pretty much the layout of all these things. Two pictures, what you're given, what you want, an equation, differentiate, solve. All right? So that's kind of what this sheet allows you to do, is kind of put all that information together. All right? So let's take a look at the screen over here. I'm going to make it dark in here so everyone can see it. I'm going to start with this example here. I'll make it bigger. Just give me a moment. Yeah. Oh, come on. Come on. Why is it not? There's a lag. This is really hard because there's a lag. It won't let me do it if it's not all on the screen. Well, that's a real pain in the ass. All right, I'm going to have to make it smaller. Okay, so what we have here in this picture is, imagine that I have a ladder or something up against this wall, okay? And what I'm going to do is I'm going to grab the bottom of the ladder and I'm just start pulling it away from the wall, all right? And I'm going to pull it at a constant speed, all right? So I'm here, I've grabbed the ladder and I'm just pulling it at a constant speed. What I want you to pay attention to is the top of the ladder and look at the speed of this point as it goes down. In the beginning, it's moving very slow, isn't it? But the further away that bottom of the ladder gets pulled away, the faster that point moves. Do you see that? Do you all see that visually? Yes? So I'm pulling this point at a constant rate. But this is not coming down the wall at a constant rate. Agreed? So what I'm going to ask you is this. As I pull, when I get to a certain point, right there, let's just say, I want to know how fast that point was moving down the wall. So at some instant in time, I want to know at that instant how fast that point was coming down the wall. Does that make sense to you? You sure? All right. So let me set up the problem. I'm going to write the word problem up on the board first. And we'll just let that sit there and play. All right? So it's really important for everyone to understand that the rate that the point is coming down the wall is not constant, right? That point coming down the wall is speeding up, right? So the speed of that point is changing. It depends on where I am, right? How far I pulled the ladder away. Okay, here we go. A 20-foot ladder is positioned on a wall as shown. Okay, so as shown here, all right? So we got this wall up against, this ladder up against the wall. The bottom of the ladder is pulled away from the wall at a constant rate of, let's go, 2 feet per second. So that's how fast I'm pulling the bottom of that ladder away from the wall, at 2 feet per second. And that's constant, me pulling on the bottom point over there, all right? At the moment the bottom is, let's say, 8 feet from the wall. How fast is the top of the ladder coming down the wall? Question. Does that word problem make sense to you? Now, the reason I'm starting with this example, there's 2 reasons. One, it's like every Cal 1 student needs to see the ladder problem, okay? It's a classic problem. The other reason I'm doing it is because it's one of the easiest ones to see what's going on. Like, you can see that we're pulling the bottom of the ladder away at a constant rate. It's very easy to see that I think it's easy to see that the top point speeds up, right? Some of the problems we're going to do after this is not so easy to see these relationships. You just have to go and do the math. Are there any questions on the word problem itself? Okay. So let's look at the sheet that I gave you, the blank sheet. We're going to go ahead and fill one of those out right now. All right. So the top left box says instant, right? See that? Instant, exact moment in time. I'm going to draw a picture in that box. It's going to be a picture of that ladder at the moment that they're talking about in this problem. So it looks like this. I have a wall, I have the ground, right? I have my 20-foot ladder. This is 20, isn't it? And this distance from here to here is 8. If you want to put feet, you can. You don't have to. I'll put feet, though. But that is the moment in time, isn't it? Read the problem. At the moment, the bottom of the ladder is 8 feet from the wall, right? So there's the bottom of the ladder, 8 feet from the wall. That's the instant in time. Yes? Okay, good. Just a quick analysis of this. It's a right triangle, right? That's a right triangle. That might be helpful later, who knows. If I drew a right triangle like this, then I could figure out what this side is, right? Because I have 2 sides of a right triangle, I can always get the third. So I might need it later, I might not, I don't know, but I'm just starting to think ahead that, you know, what things do I know, what things do I not know, right? Okay, now, that's our first picture. Our next picture, this is the instant. The next picture is our general picture. So our general picture, you have to imagine that everything is in motion, okay? So that things are moving, which means you can't lock that bottom of the ladder to be 8 feet from the wall. It's just some arbitrary position, okay? It's just some arbitrary position. So I'm going to draw the wall, draw the ground, draw my ladder. I don't know, I'll draw it like this. Make that 20. And now this position, right, the distance from the bottom of the ladder to the wall is no longer 8. It's just whatever, right? So since it's whatever, I'm going to call it x, because it's a variable. It's changing, right? This distance right here, I call x. Yes? Again, we have a right triangle. By the way, when you're filling this out, it's not step 1, step 2, step 3. It's like you can do this kind of in any order you want. You can start drawing a picture, then go put down some information that you know, just go back and forth. It doesn't have to be done in this order. Over on the side, I have something that says what you are given, right? All right, so when you're thinking about what you're given, you want to be looking for a derivative. So are you given a derivative over here? 2 feet per second, okay? So remember, derivatives are speeds, right? Rate of change. That's what a derivative is. It's the rate of change of something, instantaneous rate of change. This right here is a speed. How do you know? Feet per second, right? That's the speed that what is changing? The x, right? That's how fast x is changing. With respect to what, though? Time, right? With respect to time. With me? So I'm going to write this down. I'm given the instantaneous rate of change of x with respect to some variable of time that is just a clock running in the background, right? And I'm given that that's what? 2 feet per second. That's not how long this is, right? That's not how long this is. That's how fast this point's moving. If you were to look at that point, it's moving in that direction at 2 feet per second. Yes? Okay. Along with what I'm given, I'm also asked, also on that sheet says, what do we want? So what do we want? Okay, dy dt, I don't see a y anywhere. You're ahead of it. You need to draw that though, right? So what are we looking for? At the moment, the bottom of the ladder is 8 feet from the wall. How fast? How fast? Fast is a speed, right? Like we're talking about a speed here. I want to know the speed at which what? The top of the ladder is coming down the wall. Well, you need a picture of that in your drawing, right? Like what is that? That point coming down the wall in this general picture, right? You're trying to figure out how fast that's going down, right? You want to know how fast that point's moving down, yes? So we want to know how fast this is shrinking, yes? So we need to label this distance from here to here something. Let's call it y, right? Now we're going to draw it in this picture here and call it, let's call it y, like that. And by labeling it y here, now I can come over here and say that I want what? Dy dt. I want to know how fast y is changing with respect to time. I want to know that, right? And when do I want to know that? It's at a specific moment, right? At what's 8 feet? When x is 8 feet, right? So I'm going to say, we could talk about time. I'm just going to put here at x equals 8 feet. You got it? Read the problem. Draw a picture of the instant. Draw a picture of the general situation where things are in motion. Assign variables where you need. Write down what you're given. Write down what you want, and write down the moment that you want it. This is all the information we need to do the problem. Any questions? Once you have the basic structure here of the word problem, you know, everything in position, what you're going to do now, your goal is to find an equation. Okay, and this can be the hardest part. This is usually the hardest part. Is to find an equation, any equation you can come up with, okay? Any equation that you can think of that somehow connects the variable x to the variable y from your general picture. So can you think of any equation out there that would connect the x variable to the y variable?
Circle, x squared plus y squared equals the radius.
Circle, how about just the Pythagorean, right? Like a squared plus b squared is c squared, right? The Pythagorean identity, wouldn't that connect these together?
Yep.
So that would be x squared plus y squared is 400, right? That's what we would have?
Yeah.
Okay, so the equation that I have here, so that's one of your things on your sheet too, right? An equation. The equation I have is x squared plus y squared is 20 squared, which is 400. Now, why is it that I want to connect the x and y together into an equation? Well, because I'm trying to find dy dt, right? And I know dx dt, so if I somehow have an equation that has x and y together, I can differentiate it with respect to t, and I know that both of these are going to appear, right? Now, we just did that problem, didn't we? That's what we started class with. So we've already done the work for this, but we're going to go through it again. All right, so at this point, we have the equation, and now I think there's a thing there for, does it say implicit? Yeah, you have your equation, and then below it says implicit. So now we're going to take this, we're going to do implicit, and we're going to do the derivative with respect to t. So the derivative with respect to t of x squared plus y squared equals the derivative with respect to t of 400. Now, I'm not going to go through all the work, okay, because we already did this. So I'm just going to go to our answer. Our answer was well, wait a minute, hold on. What are we solving for? We're solving for dy dt, right? See that? So remember when I started class, I said, let's find dy dt? I knew that we were going to need it in a minute. So we know dy dt. Well, you know what? Let's do this. I'm going to change it up a little bit. Let's just act like we differentiate that. Let's not act. Let's do it. Okay, I'm going to differentiate that. All right, remember that step? Right, we did that step. That's the differentiation, right? And then we solve for dy dt. What I'm going to do a little different right here is this. I'm going to look at this result right here, and I'm going to start looking at what is it in here that I'm trying to solve for? What is it that I'm given? Am I missing any information? So as I start looking at this equation, do I know now what the value of x is at the moment in time we're talking about? Yes, it's going to be 8, right? So I can say here that for this x, check, I know what it is, right? How about dx dt? Do I know what that is?
Yes.
Yes, at the moment in time, I know it's 2, right? So check, I know what that is. All right, how about y? Do I know what y is at this moment in time? No, right? Here's that moment in time. Do I know what y is? No, but I said I could get it if I needed it, right? So we actually are going to be able to get this, but we're going to have to work for it a little bit, all right? So I'm going to put here kind of like Yes, but no, right? We don't know it directly right now, but we can find it. Yeah, so yes, but no. And then what about dy dt? Do I know it? No, but that's what I'm looking for, right? So I'm happy to see this as well because I'm solving for this. I know what this is. I know what that is. And I'm about to tell you what y is because I'm just going to go over here and solve this triangle. So I will have everything in this equation replaced except that. Understand? So I'm going to put here, I need y, right? So I'm going to go to my instant in time, call that y, and then just use Pythagorean, right? 8 squared plus y squared is 400. So y squared is 400, take away 64 is 3, what is it? 36, 336. Subtracting 64 on both sides, and then take the square root of that. Let's go ahead and do that on a calculator. Take the square root of that, and let's get a decimal answer. So someone please, if you could, take the square root of 336. Got it? 18.33? Close enough? So approximately 18.33. So where it says scratch work here is where I'm doing all this, like, you know, if I need to get y, I'm going to go do this scratch work, okay? Y'all with me? All right, let's solve the problem, all right? We're going to replace everything. So I have here 2 times x, which is 8, times dx dt, which is 2, plus 2 times 18.33 times dy dt equals 0. So getting my calculator, what's this? This is 32, right? 32. Take it to the other side of the equation, make it negative 32. And then 2 times 18.33, 36.66. So where am I here? I'm going to erase this. So we have 36.66 times dy dt equals negative 32. And then now divide both sides by 36.66. And you get, what, 0.872, something like that? Y'all getting that? Negative? Approximately negative 0.873, let's say. Yes? Now, this is the rate at which y is changing with respect to time. So this is a derivative, right? This is a speed. So I need the units on this.